Having provided us with powerful tools to contemplate the confines of space and time, revealing the stories written in the light of the universe, the entry into the 1980s symbolized the dawn of a new era for astronomy. Telescopes, as portals to places that hide the answers to the great mysteries of nature, were allowing us to see farther into space and time than we had ever dreamed. Our eyes in the darkness, a window into the complex dance of galaxies and the secrets hidden in the oceans of the universe. With this technology, astronomers began to understand the large-scale structure of reality, the architecture upon which the pillars of everything that has been, is, and will be rest. The galaxies, islands that protect the light and give meaning to the universe, were not distributed randomly. They formed a cosmic web of filaments, clusters, and vast voids. On the most colossal scales, an architectural complexity flourished. Like a symphony of light and darkness, the foundations of nature expanded through space and time. A revelation that gifted us a new canvas of reality and showed us the path to follow. The discoveries about this cosmic web motivated a search for the holy grail of modern cosmology, a map of the large-scale structure of the universe, an atlas of the pillars of nature and the place that the Milky Way, our island of light, occupies in that architecture alongside the 2 trillion galaxies that inhabit the seas of space. With the hope of being part of that achievement, the American astronomer Robert Kirshner developed a project aimed precisely at mapping the galactic distribution of the cosmos through the study of the redshift of galaxies around us. This phenomenon occurs when a light source moves away from the observer, causing the electromagnetic frequency to shift towards the red range. If they could mark the location of galaxies in different regions of the sky and see how the light of each of them shifts to red due to the expansion of space, they could know how far away they are, and therefore obtain a 3-dimensional map of the universe. Thus, in 1981, along with Paul Schechter, Augustus Eumler, and Stephen Schechtman, and using the Mayall telescope at the Kitt Peak National Observatory in the Sonoran Desert, Arizona, he began this scrutiny of the skies. They were contemplating the light of galaxies at the confines of space to obtain that atlas of the cosmos. However, upon completing the scan of the firmament and finally analyzing the results, they found something strange among all that data. In the constellation Boötes, 700 million light-years from Earth, a blank space appeared. A nearly perfectly spherical region with a diameter of 330 million light-years with very few galaxies. Such an expanse should be inhabited by between 2,000 and 10,000 galaxies. The data spoke of just 8 islands of light in the middle of a colossal desert of darkness. A sphere of void, which until then had remained hidden under its own shadow, had been unveiled. Aware of the magnitude of their discovery, that such a cosmic void challenged all conceptions of the evolution and structure of the universe, Kirshner and his colleagues published an article in the astrophysical journal Letters, showing the world what they themselves had dubbed the Great Nothing, a desert at the confines of space and time.
El descubrimiento generó gran interés y algo de escepticismo en la comunidad científica. El vacío de Boötes, como sería llamado después de la publicación del artículo por la constelación en la que se encuentra, era demasiado grande. Estamos hablando de una esfera de vacío en cuyo diámetro cabrían 3.300 vías lácteas puestas en fila. En ese momento, los modelos cosmológicos no contemplaban supervacíos tan grandes, pues esperábamos una distribución más uniforme de las galaxias. Las simulaciones contemplaban supervacíos de como mucho unas pocas decenas de millones de años luz de diámetro, jamás los 330 del vacío de Boötes. O se trataba de una anomalía o a través de ese desierto, el universo nos estaba pidiendo que reescribiéramos la historia de su nacimiento.
In the months following Kirshner's groundbreaking discovery, the international astronomical community turned its gaze towards that void reigning in the heart of the constellation Boötes. And with each investigation, with each scan of that desert of darkness, the skepticism faded. Although a few more galaxies were found, the galactic density in that 330 million light-year radius remained unusually low. The Boötes Void was an unquestionable reality. Although its existence conflicted with models of the universe's evolution, we could not deny the evidence. Now it was our duty to find the cradle of the great nothing. And as if by fate, someone formulating new mathematics for the dawn of the universe accommodated this void. A few years earlier, in the 1970s, Alan Guth proposed an extension to the traditional Big Bang model that resolved the inherent inconsistencies of a theory that was still in its early stages. The young theoretical physicist developed a theoretical framework suggesting that a fraction of a second after the germination of space and time, the universe underwent an exponentially rapid expansion. Something he himself dubbed cosmic inflation. The theory was based on the existence of the inflaton field, a hypothetical quantum field that, before the dawn of the cosmos we know, permeated a higher reality, containing immense potential energy due to a quantum fluctuation. This field underwent a phase transition to its minimum energy state. The inflationary period had just germinated, with the inflaton field in a high-energy state known as a false vacuum responsible for a fierce expansion. This inflation postulated that for a very brief time, approximately 10 to the minus 36 seconds, the universe expanded at a rate much faster than the speed of light. In that tiny time, it went from being a singularity to having a size of several light years. After that fraction of a second, the inflaton field reached its minimum energy state, a true vacuum, a transition in which a large amount of energy was released, converted into particles and radiation. The inflation stopped, giving way to the hot and dense period of the conventional Big Bang and the expansion that remains unstoppable today.
En cierto sentido, la teoría de la inflación añadía un prólogo a la historia del nacimiento del universo. Sus fundamentos, sólidos matemáticamente, daban solución a los problemas del modelo tradicional del Big Bang, y aunque en un primer momento nadie fue consciente de ello, ofrecían una explicación al origen de ese gran desierto que habíamos hallado.
With the publication of Alan Guth's inflationary theory in 1981, the same year as the discovery of the Boötes Void, many saw it as a hope for understanding how that region, whose existence was impossible with previous models of cosmic evolution, could have emerged in the dawn of reality. In a time before time, in a place without space, the seed of the cosmos flourishes in the quantum heart of the inflaton field. And in that almost flat sea, small random fluctuations imprinted on the fabric of nature decide the fate of everything that will be. Tiny quantum fluctuations that prevent the energy distribution from being uniform, amplified by the inflation itself, condemned to leave their quantum realm, to extend to macroscopic scales. That rapid expansion, which has stretched space-time itself, has carried with it the tiny fluctuations. The inequalities have been amplified, and the distribution of energy and matter in what in an instant had become a vast empire was tremendously uneven. The quantum fluctuations have led to regions of low and high density. And with the abrupt end of that inflation, with the Big Bang we know conducting the symphony, they have given us the canvas on which to paint the universe's masterpiece. In the first minutes after its birth, space fills with plasma, a primordial state of the cosmos too hot to allow the formation of atoms. The energy is so immense, the particles move so fast that even gravity cannot hold them. Light, as we understand it, with photons imprisoned in that plasma prison, has not yet been born. But something is lurking in the darkness. A mysterious, invisible substance capable of freely navigating that fierce ocean of energy. Attracted to the paths marked by the amplification of quantum fluctuations of the primordial universe, dark matter is raising the pillars of the universe. Following the path of those density differences, it weaves a structure that connects all corners of that dark cosmos. The cosmic web is being born, patiently waiting for its moment to sculpt the universe we know. And finally, when 380,000 years after the Big Bang the temperature dropped to a tipping point, everything changed. Protons could capture electrons. The first hydrogen atoms were formed. The universe had entered its recombination era. Everything became transparent. Matter sought its place in that sea. And someone was guiding it silently in those shadows. Dark matter, through its gravitational influence, was driving that primordial gas towards the filaments of the cosmic web. Gravity was sculpting the pillars of the universe, creating the architecture of nature. For millions of years, the cosmic web attracted more and more matter. Those ancient quantum fluctuations had allowed the cosmos's great work to be raised. Filaments had been created that crossed all of space where stars would germinate, where these would eventually find a gravitational refuge forming galaxies, and where these islands would create the great metropolis of light in the universe. But far from that gravitational refuge, vast expanses of space were left unprotected, condemned to be unable to fight against the density of the cosmic web. Deserts germinated in the outskirts of the cosmic web empire. Gravity had accumulated all the matter in those pillars, emptying everything that did not have enough density. Those less dense regions, determined during cosmic inflation, became cosmic voids. Areas almost devoid of matter that extend around the fragile and delicate strands of the cosmic web. Like a honeycomb, the galactic clusters form the walls, and the voids, the cells. Over time, with the expansion of the universe, the voids grew as everything gravitated towards the larger luminous structures. Everything wanted to go to the light. They were doomed to remain as deserts forever. The great voids, like the Boötes Void, are the large cavities between the filaments. Ancestral imprints in the fabric of the universe etched in its early moments.
Con este modelo, los vacíos cósmicos eran un reflejo de las condiciones iniciales establecidas por la inflación. A lo largo de miles de millones de años, lo que en un principio eran zonas subdensas, se expandieron y despejaron, creando esos grandes vacíos en la distribución de la materia. El problema es que para el caso concreto del vacío de Boötes, incluso considerando esas fluctuaciones cuánticas, este seguía siendo demasiado grande. No había habido suficiente tiempo en el tiempo como para que tal desierto germinara, algo que abrió las puertas de la especulación de par en par.
With the mystery surrounding the Boötes Void strengthening and solidifying as one of the greatest enigmas in cosmology, explaining the origin of a colossal desert too large to have formed by the simple natural evolution of the universe, was becoming one of the community's top priorities. And with all the paths leading to dead ends, there seemed to be only one place to find the answers. Many began to conjecture that the existence of the Boötes Void was only possible if it harbored a monster at its heart. A then hypothetical entity, a guardian of light roaring from the bowels of space-time. In 1951, at a time when secrets emerging from general relativity were still being discovered, American mathematician and physicist Martin Kruskal was exploring the mathematical foundations of Einstein's formulas when he realized something that we had overlooked for nearly 40 years. In the numerical basis of black holes, bodies defined by the absence of themselves, by the existence of a singularity with the power to drain light from the universe, there emerged the possibility that this singularity, this corrupted heart, caused an expansion outward. The mathematics made possible the existence of what he understood to be the inverse of black holes. If the singularity of those guardians of darkness was a well that absorbed everything that ventured beyond its event horizon, the singularity of those mathematical opposites would be a fountain from which matter and light constantly emerged. If nothing could escape a black hole, nothing could enter this body. Kruskal named these entities white holes. aware, however, that they were nothing more than mathematical curiosities, tales that emerged from playing with Einstein's equations. Even so, some saw in them an answer to another of Einstein's predictions. The mathematics of general relativity allowed for space-time to deform to the extreme of connecting two very distant points in our three dimensions through a passageway. Passages in the fabric of the universe known as Einstein-Rosen bridges. Shortcuts in space and time. Tunnels that connect two regions of the universe separated by tremendous distances. This prediction was associated with black holes, whose singularity could be the entrance to those passages, but there was not a single object that could represent an exit. At least, not until the theorization of white holes. Following this conception, American theoretical physicist John Archibald Wheeler developed the hypothesis of what he called wormholes. A reimagining of the Einstein-Rosen bridges in which a black hole would be connected with its temporal counterpart, that white hole, through a theoretically navigable passage in space. Mathematically, everything fit. The wormhole hypothesis even allowed us to understand where everything swallowed by a black hole, which seemed to be lost in nothingness, went. However, these passages would be extremely unstable. Any disturbance, even at the quantum level, would cause them to collapse and close quickly. This, along with the fact that not a single observational piece of evidence for the existence of white holes had been captured, relegated everything to the realm of speculation. But this last point might have just changed. The Boötes Void might be giving us that signal. One of the main hypotheses proposed to explain its enormous size is that at the heart of that desert rests a white hole. A fountain that, through its relentless expulsion of matter over billions of years, has pushed all the stars out of its realm. The theory posited that in the middle of the void, one of these bodies is releasing everything swallowed by a black hole in another part of the universe, and transported to Boötes through a space-time passageway. It's not that gravity prevented matter from reaching that region. It's that a monster of light would have expelled the thousands of galaxies that should inhabit it out of its realm.
Aunque hubo especulaciones iniciales, no se encontró evidencia concreta de la existencia de un agujero blanco en el vacío de Boötes. Por muy fascinante que fuera la teoría, esta no estaba acompañada de ningún respaldo empírico. El problema es que sin ella nos quedábamos sin explicaciones naturales. No había nada en el universo que pudiera vaciar tan colosal desierto. A no ser que alguien se hubiera encargado personalmente de ello, que otra forma de vida estuviera detrás de su nacimiento.
At a time when the search for extraterrestrial life was ceasing to be a utopia and transforming into a real scientific ambition, astrophysicist Nikolai Kardashev became the visible face of that odyssey in the Soviet bloc. In 1964, the Russian scientist organized a conference at the Bayurakan Observatory in Armenia, where he gathered the great luminaries in the field of radio astronomy to find viable techniques for detecting extraterrestrial signals, something that involved understanding what we were looking for in that darkness. To that end, Kardashev developed a method for categorizing civilizations, a way to classify any hypothetical civilization in the universe according to a single parameter: their use of energy. At that conference, he presented to the world what he had named the Kardashev scale, measuring the degree of technological evolution in 3 categories based on the amount of energy a civilization can harness from its environment. Firstly, and as the one towards which we ourselves are transitioning, a Type 1 civilization is one that has managed to dominate its home planet. It controls and uses at will all the energy available from its world through absolute power over its resources. With this energetic dominance, if they have not perished as victims of their desire for growth, the beings will inevitably turn their gaze to the skies. They will not be content with their small planet, and will have begun the path towards a new class of civilization. Because secondly, on that scale, a Type 2 civilization is one capable of mastering its parent star, of harvesting all the energy from its sun through a megastructure that goes beyond our dreams. turning its entire system into a colossal mine, sacrificing the life of its sister worlds, they will have initiated an evolutionary leap comparable to the discovery of fire, the construction of a swarm of solar collectors, a sarcophagus around their god of light, about 30 quadrillion panels constituting the structure of what was named a Dyson sphere, a titanic creation that would grant them the power of a star. And with that power of the gods in their hands, they will have torn down all the barriers of space and time. There will be nothing to stop them. The transition to the most advanced form of life in the universe will have begun. One capable of making light disappear, and of germinating deserts of void. Third and lastly, a Type 3 civilization is one that has managed to dominate an entire galaxy. That will have harvested the energy from each and every star in their island of light. Interstellar travel, made viable by their enormous energy power, would mean that it would only be a matter of time and resources to achieve that galactic dominance. And at that point, they could, in theory, make an entire galaxy go dark. With that tyranny over all the stars, they could have consumed them one by one. They could have taken away the last light from a galaxy and, with ambitions that transcend our poor human consciousness, ventured into the intergalactic medium to colonize new islands of light. Like parasites spreading through the universe, exhausting the last light of dozens, hundreds, and thousands of galaxies. A virus that it was theorized could be behind the germination of that great desert. The hypothesis that a Type 3 civilization was behind the creation of the Boötes Void had just shaken the foundations of the scientific community. Perhaps that desert was not empty. Maybe we were contemplating the corpses of countless stars hidden in their own darkness. Deprived of light since ancient times. A galactic cemetery, with gods having perished before the power hunger of a civilization more powerful than the stars themselves.
La teoría de una civilización de tipo 3 alimentándose de galaxias a medida que se expande por el universo podía llegar a tener sentido. Incluso podría explicar la esfericidad casi perfecta del vacío de Boötes, con la civilización expandiéndose desde el centro. Sin embargo, cuando los astrónomos exploraron las galaxias cerca del borde del vacío, no encontraron reducciones en la luminosidad de las estrellas que podrían ser indicio de la existencia de esferas de Dyson. Algo que redujo las ilusiones y que nos obligó a estar mucho tiempo sin ninguna nueva explicación al origen de ese vacío.
In 1997, through observations whose level of detail could not be achieved at the time of its discovery, astronomers found a thin filament of 60 galaxies extending as a linear structure through the Boötes Void. It was still a very small number of galaxies, but that galactic strand connecting two regions of the cosmic web had enormous implications. From the 8 galaxies we thought existed, we had increased to 60, which formed a kind of tube near the center. That structure within the desert was identified as the remnants of the boundaries of 2 smaller voids, fused as they grew into each other. The echoes of a barrier that once existed between 2 voids, now thinned into an almost imperceptible strand. A tiny group of galaxies lost in the largest void in the universe. The discovery of the galactic filament led scientists to theorize that the Boötes Void formed from the merging of 2 smaller voids. Something that would explain its almost perfect spherical shape, like 2 soap bubbles fusing, leaving the galaxies on the edges of each of them on the shore of a cosmic abyss.
Las galaxias estaban tan aisladas que en caso de que la Vía Láctea se encontrara en tal paraje, no habríamos sabido que existen otras islas de luz en el universo hasta los años 60. Cuando la tecnología ya habría permitido atravesar ese mar de oscuridad. De todos modos, esa fusión de vacíos seguía sin explicar del todo su origen. Nos estábamos acercando, pero faltaba una última pieza, algo que llegó a través de una oscura entidad que impregna los cimientos de la realidad.
In the mid-1990s, a group of astronomers began a study on Type 1a supernovae. These stellar eruptions emerge from binary systems due to the battle between two sisters. A white dwarf, the corpse of what once was a star, and a red giant. In this realm, when one of the sisters has died while the other is still alive, only one destiny exists, a shared future. Trapped and condemned to dance, the white dwarf starts to behave like a cannibal. A star devourer that, with an immense gravitational power born from the compaction of its dying core, attracts the gas and plasma of the red giant. Hydrogen is accumulating in its atmosphere in a countdown to a point of no return. When its mass surpasses the Chandrasekhar limit, the stolen material compresses the carbon in its depths, reigniting its heart. The white dwarf's innards light up, carbon undergoes nuclear fusion, and an enormous amount of energy is released. It has exploded in one of the most powerful and violent events in the cosmos. A Type 1a supernova has just emerged, shining like 5,000 million suns. These are the only stellar explosions that always shine the same way, a perfect homogeneity that makes them beacons in the darkness. Depending on how bright or dim we perceive the light, we can determine the distance that separates us. With this principle, that group of astronomers used them to measure the largest distances in the universe. In 1998, after finishing the study, they detected a redshift much greater than expected according to the standard model of the cosmos's expansion. The galaxies were moving away from us faster than they should. They had just discovered the accelerated expansion of the universe. Something, unknown at the time, was causing the space between galaxies to grow rapidly. An inevitable entity we named dark energy. Unlike the matter we know, which tends to slow the expansion of the universe due to the gravitational attraction between bodies, this dark energy would exert a negative pressure behind the undeniable acceleration of space-time. This force, which would represent 68% of the total energy matter content of the cosmos, was pushing the universe to grow. The oceans of darkness between galaxies were becoming increasingly larger, and the pillars of the cosmic web were isolating more and more, heading towards the eternal night.
El descubrimiento de la expansión acelerada del universo añadía una nueva esperanza. La aceleración afectaría la evolución de los vacíos cósmicos, haciendo que se expandieran y que se volvieran más vacíos con el tiempo. Introduciendo esa constante cosmológica en los modelos, la existencia del vacío de Boötes era al fin posible. Vacíos así eran una prueba de la inevitabilidad de la energía oscura y, de hecho, una posible explicación a su origen.
Since that revolutionary discovery of the universe's accelerated expansion, the scientific consensus was that dark energy emerged as an intrinsic property of space-time. It was born from the vacuum itself, permeating the foundations of reality with an exotic and undetectable form of energy. Nevertheless, its existence is inferred from observations of expansion in an attempt to preserve the fundamentals of general relativity. It has never been directly observed, and there is not a single clue about its nature. An open path where a team of astronomers found a way to, through cosmic voids, reformulate all preconceptions about this entity. In 2019, a team of Iranian scientists led by Ebrahim Yusofi proposed that cosmic voids, these regions of space with an extremely low matter density, could be playing a key role in the accelerated expansion of the universe, influencing the dynamics of space in a way not previously considered. The physicists were suggesting that dark energy might not be a form of energy inherent to space. It would not be an entity as such, but the manifestation of the geometric properties of these deserts. Cosmic voids, due to their very low density, could have unique gravitational effects. These voids could generate a kind of negative pressure that would result in the acceleration of cosmic expansion, with an effect similar to what we had historically attributed to dark energy in the lambda CDM model, the model of evolution that, until then, matched all observations. According to their theory, cosmic voids would exert a surface tension on the filaments of the cosmic web where galaxies find their home. As voids grow, they put more and more pressure on the strands, a self-reinforcing effect that would explain the observation of that accelerated expansion. Essentially, the scientists were suggesting that what we call dark energy is nothing more than the sum of the effects of all the cosmic voids in the universe. Their findings were published in January 2022 in the monthly notices of the Royal Astronomical Society, showing that numerical simulations and theoretical models made it possible for these great voids to be driving the universe's accelerated growth.
Aunque la teoría es innovadora y ofrece nuevas perspectivas para la aceleración del universo, todavía hacen falta muchos estudios para confirmarla o refutarla. La comunidad sigue explorando explicaciones al origen de la energía oscura, y esta es solo una de las muchas que están siendo investigadas. Igual que la posibilidad de que uno de estos grandes desiertos resuelva el que ya ha sido bautizado como la gran crisis de la cosmología.
When we discovered that the universe was expanding at an accelerated rate, the scientific community focused on answering the big question that emerged from this finding: the rate at which it expands. This is what we call the Hubble constant. After many years of increasingly reliable measurements, the pinnacle of this odyssey arrived in the spring of 2013. With unprecedented resolution and sensitivity, the Planck telescope had spent 4 years mapping the oldest light in the cosmos. An instrument designed to analyze the cosmic microwave background, CMB. This ancient radiation permeates the entire observable universe and originates from the era of recombination, that moment when the first photons were released from the opaque ball of plasma that was the primordial cosmos. Planck was observing the farthest point in space and time that we could physically see, rewinding to the very dawn of light, allowing us to contemplate in full splendor that ephemeral radiation imprinted with the birth of the universe. Finally, on March 21, 2013, the European Space Agency organized a conference to present the most complete and detailed image of the cosmic microwave background to date. That snapshot revealed much information, including the universe's rate of expansion. The image from Planck had just provided the most precise measurement of the Hubble constant, giving a value between 67 and 68 kilometers per second per megaparsec. We had obtained this measure of the universe's acceleration. It seemed that a long chapter in the history of cosmology was closing. But there was still one last sentence to be written. 3 years after Planck's historic image, a team of scientists led by the American astrophysicist Adam Rees began a study to confirm the Hubble constant predicted by CMB models through direct observation. If our model of the universe's evolution was correct, measuring the space's acceleration near our galaxy should yield a value very close to what had been obtained by inspecting that ancient light. Otherwise, something fundamental in our understanding would be failing. Using Type 1a supernovae, which had revealed the cosmos's acceleration 20 years earlier, and Cepheid variables, stars that pulsate radially and vary in both temperature and diameter to produce very regular brightness changes, Rees and his team managed to obtain this acceleration rate in our local universe. The Hubble constant was between 73 and 74 kilometers per second per megaparsec, far from the value Planck had shown through the cosmic microwave background. The worst fears had just been confirmed. There was a discrepancy between the two measurements. The scientists published their study results in the Astrophysical Journal, highlighting this discrepancy between local measurements and those derived from Planck's image. Depending on where we looked, the universe seemed to expand faster or slower.
Este conflicto entre las medidas locales y las cosmológicas deducidas del fondo cósmico de microondas es lo que se conoce como la tensión de Hubble. y aunque se ha sugerido que una nueva física desconocida podría estar detrás de ella, es posible que la solución nos conduzca a uno de esos grandes vacíos, a que nosotros mismos vivamos en el corazón de un desierto cósmico.
With the Hubble tension becoming one of the biggest problems of recent times and many hypotheses trying to explain the discrepancy between the Hubble constant values, a group of astronomers attempted to find that explanation through cosmic voids. A large supervoid could affect the apparent speed at which local galaxies seem to be moving. Hence, the conflict between the cosmological value and the local value, distorted by the impact of a void. If the Milky Way were in a void or at least near one, the nearby galaxies would seem farther away due to the lower density of matter contributing to faster local expansion. Essentially, if our island of light inhabited a void, we, from its heart, would see a local value for the Hubble constant higher than it actually is. Precisely what was happening with that discrepancy in the expansion rate. Under this premise, a team led by astronomers Ryan Keenan, Amy Barger, and Lennox Cowie used data from Type 1a supernovae to map the distribution of matter in large regions of space. Against all odds, even though the mere premise was considered too strange by the community, they found evidence of a void. The Milky Way inhabited very close to a region with a significantly lower matter density than the universe's average. Our home in that ocean has far fewer galaxies than the surrounding regions. Our island of light is a few hundred million light-years from its center, sheltered in the Laniakea supercluster on the edge of that abyss. We inhabited the vicinity of a desert named the KBC Void, after the initials of the discoverers' last names, with an approximate diameter of 1 billion light-years. Making it one of the largest known voids in the universe. Much larger than the Boötes Void itself. The discovery of the KBC Void was published in the Astrophysical Journal in 2017, detailing the analyses that led to the void's identification and its impact on modern cosmology. The presence of such a large and close void could have implications for local measurements of the universe's expansion rate, thus resolving the Hubble tension. The value obtained from the cosmic microwave background, from that ancient light unaltered by our location, described reality. The local value, distorted by the proximity to that abyss, was merely a trick, a mirage in the middle of that desert.
Si nuestra Vía Láctea y las galaxias cercanas habitan la frontera inmediata de un vacío tan colosal, era lógico que la expansión local del espacio pareciera más rápida de lo que en realidad es. El vacío de Boötes después de tantos años nos había inspirado a descubrir que nosotros mismos vivimos en las cercanías de uno de ellos, algo que reavivó el interés por unas regiones que considerábamos muertas, puro vacío, y que sin embargo podían incluso abrir la puerta de los mundos más allá del horizonte.
In the 1980s, Alan Guth's inflationary theory, which made the existence of cosmic voids possible, became a phenomenon within the international community. So much so that during the Cold War, two of the Soviet Union's most renowned scientists took up the mantle from the American physicists to explore the cosmological foundations of this model about the universe's birth. In 1981, physicists Andrei Linde and Alexander Vilenkin delved into the elegance and simplicity of this inflation, realizing something Guth had overlooked. In his theory, nothing explained what caused the inflation to stop, giving way to the Big Bang we knew. After months of attempts to detail this cessation, always ending in dead ends, only one option remained. The only answer that fit the complex mathematics was that inflation never stopped. The theory described how this expansion occurred while the inflaton field's energy was high. But as it shed that energy, the same quantum fluctuations in which the universe's seed blossomed could repeat. An endless cycle of fluctuations that expand their space at an enormous rate. The inflaton can never shed all its energy. In each inflationary process, quantum fluctuations await to expand space again. Something that will happen repeatedly, for all eternity. Linda and Vilenkin had just reformulated the model through a theory they named eternal inflation. Inflation does not stop throughout space. It ceases in some regions but continues forever in others. In a sense, in that inflaton field, new Big Bangs are constantly occurring. Our universe would be just an island of matter in an ocean from which more islands keep emerging. The physicists had provided the first theoretical basis for the existence of a multiverse. Their theory posited that there would be no beginning of time. Globally, the cosmos would be a fractal in which universes constantly bloom. Bubbles born from the pillars of space-time. Each of these is a universe in itself, with its physical properties, fundamental constants, and unique laws, depending on the conditions in which inflation stopped in its region. A collection of universes inhabiting an eternal sea, forever isolated from each other. The theory of the inflationary multiverse had been born.
Desde su concepción, el multiverso inflacionario que se desprende naturalmente de esa inflación eterna obtuvo una gran fama. Ese reino de universos ofrecía explicación a por qué el nuestro tiene las condiciones necesarias para la vida, algo que se conoce como principio antrópico, sugiriendo que nosotros vivimos en uno de esa colección, compatible con la existencia humana. Sin embargo, la teoría era muy difícil de probar, al ser imposible observar directamente otros universos. La única esperanza pasaba por tener pruebas indirectas, y para ello solo un desierto como el vacío de Boötes podía darnos lo que necesitábamos.
In recent years, several theoretical cosmology papers have begun exploring the possibility of traces of that multiverse within our reality. That in that realm beyond the horizon, bubbles might collide with each other. Impacts between universes that leave everlasting scars. The indirect evidence of the multiverse's existence. With the ambition to find where to look for these traces, cosmologist and theoretical physicist Laura Mersini-Houghton suggested that anomalies in matter distribution could be those scars from collisions between parallel universes. That cosmic supervoids would be the footprints of that multiverse. Models made it possible that low-density regions were caused by bubble collisions in their time. The Boötes Void, whose origin had intrigued us for decades, could be the scar of the struggle between our universe and another in that eternal multiverse. The echoes of the greatest battles. A war that fractured the pillars of our reality, creating a desert in space. In that perfect darkness could lie the proof of worlds beyond the horizon. The cosmologist's theory shook the community's foundations, prompting an extensive search for patterns in the cosmic microwave background that could indicate the presence of supervoids formed by bubble collisions. But despite some studies suggesting regions consistent with this scenario, the evidence is not conclusive. The dream of conquering the multiverse remains far away.
A día de hoy la comunidad científica sigue dividida sobre la interpretación de estos supervacíos. Mientras que algunos investigadores ven el vacío de Boötes como una prueba de la existencia del multiverso, otros muchos argumentan que este y otros pueden ser explicados por procesos dentro de nuestra propia realidad, sin necesidad de invocar a otros universos. Estamos aún en el terreno de la especulación, pero hacen falta muchas más noches de observar los cielos antes de poner fin a esta historia.
That great desert at the edges of space and time, which once frightened us with its colossal nothingness, had given us a new vision of the reality around us. We had always believed that the answers to great questions were hidden in the light. Now we understood that it was also in the empire of darkness where we must search for them. The Boötes Void was much more than a desolate place. In that spot where nothing happens, where nothing changes, and time has no meaning, we had found a path to decipher forces we are just beginning to understand. It had forced us to question all our conceptions about nature's architecture. In its barren heart, a memory of the oldest stories remains treasured. Because in every corner of the universe, in every star and every void, there is a tale waiting to be read. We must continue exploring these deserts where time stands still. For they are the silent witnesses to the evolution of all that has been, is, and will be.